Hello, IB. We're going to go ahead and look at series and how sigma notation kind of plays in with the different formulas that we've been using. So sigma notation is going to be a shorter way for us to basically write down the answer to a series. So when you guys wind up looking through a sequence, we know that they're just a set of numbers that have a pattern and have a common difference or a common ratio. So for example, you might see something like 1, and then the next value might be 3, and then 5, and then 7, because you're adding 2 every time, right? So that's one pattern or sequence that we can look at with a common difference. So it's an arithmetic sequence. When we look at a series, what it winds up doing is it takes all those values that are in your sequence, but it adds them together to come up with a sum. So I would add 1 plus 3 plus 5 plus 7 plus all of the other values that are in that sequence. If I have a finite number of terms in my series, then let's say I only have the first 4. So I would add the sum of 4 values. That would be 1 plus 3 plus 5 plus 7. And then I could have my answer. I could add them together. But if you have an infinite series, well, then I'm actually going to be looking at, okay, I want to add 1 plus 3 plus 5 plus 7 plus, I would want to go on to infinity. So that would mean I'd be looking for, does this sum wind up converging, or does it diverge? Does it just keep going to infinity? What winds up happening? All right, so right now we're going to focus our attention around the finite series. So if we take a look at our notation, this S stands for sum, and then that small number n just refers to whichever term in the series we're actually talking about. So how many terms are in our series? So it says we have the sum of the first n terms, all right? So when we look at our sequence, and we call this maybe u sub 1, or u sub 2, or u sub 3, as we've been doing over the last couple days, all right? For a series, we'll add those terms together. So your commas just wind up changing from a comma into a plus sign. So when we look at our notation for the example, our sum of the first term only would just be 3. Our sum of the first 2 terms would be adding 3 plus 7, so that's where we're getting the 10. The sum of our first 3 terms, that would be 3 plus 7 plus 11, so we'd wind up getting 21, because we would take 3 plus 7 plus 11, and then so on and so forth. So we could do this for as many different terms as we want, and it all depends on what that n value is. So the n denotes the number of terms, not the value of the term itself. That is going to get very tedious if we have to keep listing out as many terms as we want, or if we start to jump to a lot larger terms. So what we wind up using is sigma notation, and you guys learned little sigma, so small sigma you guys used for standard deviation in year 10, and this is capital sigma, and we use that for summation, okay? So when we see the symbol, big sigma, we're basically thinking of this as a sum of several terms, all right? And you have this value at the bottom, and you have a value at the top, and all that means is we're going to start when k is 1, and we're going to end when we get to whatever that number is on the top. So this value down here is your starting position, and then the value at the top is your ending value, all right? So when I read this out loud, I say the sum of all the numbers that are in the form of u sub k, so that could be any expression that we are given, and k is going to change. It's going to start with whatever that first number is, so 1, 2, 3, and it's going to go all the way up to whatever n is, so that's our ending point. So n is going to be any positive integer, all right? So we can call it a positive integer. So it'll go up to some value that we can easily substitute in. So let's see how that actually works. If we are taking a look at this first example, we have a starting point when r is 1, and we have an ending point when r is 7. So I'm going to say that the sum from r equals 1 all the way up to 7 of r plus 1, that will be equal to, I'm going to replace 1 for the r. So again, this is my starting point. So I start with 1. So I'll go ahead and substitute in 1 plus 1 is the value of my first substitution. And I'm going to add that to the next value of my sequence that I'm going to wind up adding together. So we'll make a series, right? So 1 plus 1 is the first term. And then I'm going to go to my next value. So I'm going to go to 2 plus 1. So 2 replaces r. And then 3 replaces r. And then 4 replaces r. And 5 replaces r. And I'm going to do this for 6. And then I'm going to go up to 7. And I'm going to stop. Because 7 is my last value that I substitute in. And now it's just a matter of adding all these values together and coming up with my total. So what I just found was the sum of 7 terms, and it equals 35. All right, so my series winds up being 35. Let's take a look at one more example. For this one, we're going to start when k equals 1, and we're going to go up to when k equals 5. Go ahead and pause here and try to set this one up yourself, and we'll also check our answers with the GDC. All right, guys, so setting this up the same way, we begin with k equal to 1, and we substitute 1, then 2, then 3, then 4, and we end on 5. So this is just a quick way of asking you to add all of the different values together when you substitute in 1 all the way up to 5. So my series of 5 terms is 31 over 32. All right, the sum is going to be 31 over 32. When you guys get to class, we'll wind up checking this. You can always use your calculator to add these together, and then we'll also go through an example using your calculator in class. So one quick way that you guys can wind up using your GDC is on your calculator where all of your options are right here, where you guys also find matrices and your fractions. There is a sigma notation that you guys can use to substitute in your beginning, your end, and also the expression that you're given. So go ahead and try this with the last questions that we did, just to make sure that you guys are getting the same answers. All right, guys, so let's go ahead and link together what we've talked about today versus what we talked about last lesson. All right, when you're given a general series and you have a first term, so this is your u sub 1, and all of your terms after that, you can also tell just by looking at the sequence or series that you have a common difference of 2. So if I were to write this exact same series using the sigma notation, I'm looking at my very first term being adding 2 to my previous number. Excuse me, adding 4 to my previous number. So already you guys can tell that your first term is 3. We have a common difference of 4. So now if we think back to our u sub n formula for a generic sequence, you guys use your first term plus n minus 1 multiplied by your common difference. So for us, that would wind up being, our u sub 1 is 3 plus n minus 1 multiplied by our common difference of 4. So our general expression winds up being 3, we'll have 4n minus 1 in order to get to that next term. Excuse me, minus 4 in order to get to that next term. And then once you simplify, so 3 minus 4 gives you negative 1, so we'll have 4n minus 1 as our general description of how we get from one term to the next. All right, so if that's going to be our general expression for this pattern that we're looking at, we'll go ahead and wind up writing it as the sum of 4n minus 1, and we'll start where n is equal to 1, and we'll wind up going up to n. So it doesn't matter what letter we use. So if you notice in the textbook, they like to use k. So here's our k value. We start with k equals 1, and we'll go up to n. Okay? So let's go ahead and take a look at what you guys are given in this last expression. Last series, we have a summation of 4k minus 1 as our term. We have start with k equals 7. We'll go up to 50. Go ahead and pause here and start to write out what your series will look like. So if you started this one, you're realizing you are not going to wind up taking all of your time substituting in 7 all the way up to 50. You're looking at several values there. So this is one that you might want to use with your GDC to go ahead and substitute in and wind up doing this a lot faster. So showing some work that you know what your first term looks like and your second and your last term, but then after you set that up, go ahead and grab your GDC and find your actual solution. So last but not least, we're going to leave you guys with an example to try on your own. But notice that if you do have an expression that winds up being a lot to handle as it is, you can wind up separating terms. So you can wind up taking the summation of the first term plus the summation of the second. So that would be the same as if you kept them as one. You can also wind up factoring out a constant. So if I take out a constant and just multiply it after you wind up doing the summation, you wind up with the same answer as if you leave it in. So just a few other rules that you guys can apply to sigma notation, just as you would when you are working with normal algebraic expressions as well. All right, so go ahead and try this last example, bring your answer to class, and we'll continue with this one next time.